was. I tried to talk and you all couldn't hear me.
Oh, is that right?
So that, yeah. So there's that possibility. I mean, they're both muted, but
I think
Like, I
you
tried
have to change the speakers. Like it
Yeah.
defaults to the computer, but you actually want like
Oh, it's right here.
something. Yeah.
Select a speaker.
Like, it's either that they can hear us, but we can't hear them. It's like that one or the one below it. It's like one of the ones that's not checked. Just try to-
Wait, no, see, I think it's just because I have the audio turned down on the room. Can you guys say something now?
Yeah, can you hear us now?
Oh, we can hear it. Yeah, so see this little control panel? It begins with speaker X, which is in the middle. So it can go up and down from that, but I don't know what down from X is, but up turns the speaker on. So it's kind of a weird setup. Okay, so we're functioning, right? I got this recording. Okay, so we can hear you guys. So if you can't see stuff, let me know. And then we'll try to fix it. I think I'm recording to the right place, and we found the other, thanks to Josh, right? Or what's your name, Josh?
Josh.
Yeah, Josh, yeah. Thanks to Josh. He saved the day, the hero of Polymer physics.
But you probably have to email it to yourself.
Yeah, well, I brought a
Flash drive.
flash drive, yeah.
Yeah.
So it converts and do that. All right, so this takes me a long time. You know, I found this paper and like you'd think that, and it's something I know something about. So you think like maybe half an hour. But I actually spent a long time going through this thing. So this is Julia Higgins. She was knighted. So she's I guess she's a dame, but I put down lady in the thing. I think they call a dame a lady, like they call a knight a sir. Is that right? I don't know. Anyway, she's a lady. So she was knighted. And she did this neutron. I mean, she's 80. She's 79. I looked it up because I thought she must be 90 something. Because I knew her, I met her, you know, a few times. And she seemed kind of old then. So we had a faculty member, Steve Clarkson, who was from Sheffield, England, but he went to school, I think in Leeds or something. But anyway, so she went to Oxford or someplace. I think she went, because I just looked at her wiki page and I said she went to Oxford and then she taught school. It doesn't say on her wiki page that she taught school though after that. So she went in and taught like grammar school or something or high school. She was Clarson's teacher. Clarson went on to become like a polymer scientist guy, you know. So anyway, she was his teacher and then she went to Manchester and fiddled around with neutron scattering. Then she went to France to the Grenoble, France, in the Alps, kind of, or whatever, the French, whatever they are, the Alps, I guess. And then did neutron scattering there, and then went back and went to this Imperial College London, which is supposed to be like one of the best schools. But then I also found out Imperial College is only from 1909. It isn't like from the 1600s or something. It's basically like a US university. You know, like those US universities much older than Imperial College, even though Imperial College sounds like it's this really old, like Cambridge or Oxford. And they act like it too. Like they act obnoxiously, you know. So basically they have a chip on the shoulder. But they should
say 1909?
1909. That's like pretty recent. Like UC's older. UC's older than Imperial College, yeah. So anyway, there you have it. So that's the way England works. England's got a pretty funny system, you know. It's nice sometimes. I can imagine living there, you might feel a little boxed in, you know. So anyway, this is what they're doing. So the paper is not about what they're doing, kind of, you know. This is the supporting information. That's the wrong supporting information. I clicked the wrong button, I think, because I already checked this. O'Connell supplemental here. This is the deal. So there's something called non-solvent. It's called MIPS or something. They use it to make membranes. Like if you want to make a polymer membrane, I guess the first one should be homework 5. So if you want to make a polymer membrane, you take a polymer in a solvent. It's in brackets here somewhere.
Yeah, you want homework 6.
Oh, jeez. All right. Like I said, I was up like late doing this stupid thing. So, and it shouldn't have taken that long, but somewhere it says NIPS here. It's NIPS, yeah. So it's non-solvent induced phase separation. So you take take a polymer, put it into a solvent. In this case, the solvent is dichloromethane, and then you dump in a non-solvent like hexane here, and that makes a polymer come out of solution. Or it can make it can make holes in it. So usually they use NIPS to make microporous membranes, like these, I don't know, filtration membranes and stuff they make by NIPS. It's like the main way to make a plastic membrane. Like the cellulose acetate membranes that are used for reverse osmosis. And those are made with NIPS. So this is like the, anyway, so they're doing NIPS here, but they're doing it kind of in a weird way. So this is also a rig that's from another field too. So this is all like 2 fields combined to do a 3rd field. The other field is biology, where you want to see like protein folding. So you take the protein and you denature it or something here. So you put it into some acid or whatever, something that's going to denature it. And you can watch it unfold on a like less than millisecond, whatever that is, like hundredths of a nanosecond time scale. And then you can study that with X-rays because you can get a high flux. You basically, if you use the X-rays are made at a synchrotron and the particles are flying around. So if you use that pulse of that flying around the ring, which is at almost the speed of light, then you can get like nanosecond resolution. You get with a synchrotron, you have enough flux, you can take almost a photograph of the molecules on a nanosecond time scale. So it's possible to do that elaborately. And the rig they're going to use is like throw 2 jets together and then look at that one spot, you know. So they take that biology, that's called, what's it called, like freeze flow or something flow mixing, some kind of, there's a name for it. It's also got an acronym like NIPS or something, right? But so when you send the 2 jets in, they meet here, then you can get the thing into the non-solvent region, precipitate out the polymer, and this could be like a dilute solution. That could be dilute. So you can get you can conceptually get like one polymer chain collapse down, and then like you can make a nanoparticle of that one molecule. So this is a goal. It's a proposal goal. Like no one actually needs this. It's like, it sounds good. Like they talk about atomic resolution spectroscopy. There's a big fields of study going on like that. So anyway, this is an atomic level. So you make 1 molecule particles. People like that. But right, a tire is 1 molecule. Okay, because it's bonded all together. So you can have 1 molecule. If it's a big molecule, it doesn't really mean much, right? But so these are 180,000 molecular weight. So it ends up being like a 10 nanometer particle that you can possibly make, right? And then it quenches down to the non-solvent. That's the idea. So it's a phase behavior issue. So you put the polymer in here. What's the structure going to be before it meets its fate? And then how do you develop this structure where you're going to get a single polymer in that single particle, right? So that's the idea of it. The polymer they choose to use is this PPPO. Okay, so it's this guy. So it looks a lot like so polyethylene oxide would be like ethyl here and an oxygen. That's when it's water soluble. So the polyphenylene oxide is just this ring, like an aromatic ring. And this is called para substitution because you're at the 2 ends of it. It's like para, ortho, meta. Not sure between ortho and meta, but that's para, right? So para is the most popular. So anyway, and then you have this 2,6 substitution. You go like 1, 2, 3, 4, 5, 6. So it's called a 2,6 phenyl substitution. So it's called polyphenylene. Poly 2,6 diphenyl paraphenylene oxide. It's a long name, PPPO. PPO PPO makes Norel if you mix it with polystyrene. So that's a GE Plastics, which became the Saudis bought the largest United States plastic manufacturer. We call it Sabex, Saudi Arabian, whatever, right, in Indiana. So a lot of these were mostly developed in New York, near Albany. What's that town? Schenectady, New York. That's where like almost all polymers. There's two places where all polymers were built, originally. Schenectady, New York, at GE Plastics, and DuPont, in Delaware, Wilmington. So experimental station, and they're Nobel laureates in both places for like developing all the polymers. Anyway, PPO was developed at GE Plastics, and then they made, because polystyrene was brittle and this stuff is tough, so you can make something like polycarbonate, and they mix. It's really strange that they mix. Like most polymers won't mix. These two mix. When you mix them, you make something like polycarbonate, and it costs like next to nothing. Like polycarbonate's like $2.50 a pound. Do you know what the price is? And this polystyrene is going to be like at 25 cents or 50 cents a pound. So basically, you can make something like polycarbonate. It's not as good, but basically, anyway, Norel is like a pretty popular polymer for various things. It's fracture resistant and stuff. So anyway, but this isn't. This stuff is used for like breathalyzer tests. Like they say, blow into the tube when the cop pulls you over. This didn't happen to me, but basically it could have easily, it never did. Basically, from movies, they say like blow into the tube. The tube has this PPPO in it, and somehow, because it's got like polarity and non-polarity, it sucks up the alcohol. And then you just warm it up and it comes out. So you can use it to concentrate your breath alcohol, and then they can get a quantitative measure from that little tube, right? You can also, you can imagine, all right, so that's going to be a surface area issue. Like the smaller the particles, the better the situation. So they use a fiber, or they make fibers out of it, and they pack that little tube with this fiber stuff, so it'll suck up the alcohol. It can also suck up like germ warfare agents, any kind of nerve gas. It can suck up almost anything, it turns out. So it turns out like this could be pretty useful, like the DOD or biomedical, if you want to test someone if they have, like diabetics, when they produce, supposedly glycol or some ketones in your breath, right? That's the main sense. You could test to see if someone's dying, like to breathe into this tube, see if there's ketones, that kind of thing. So anyway, so there's a lot of things your breath could do. So basically making these nanoparticles, there's some reason to do it. They don't mention that here. They just say like blah, 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 blah. So this is typical of Julia Higgins stuff. So it's kind of an elaborate ternary phase diagram. Green means miscible, and they call this red. Okay, so the red means immiscible. So if you go up here, you're going up in concentration to 50% polymer. You go over here, you go to 50% hexane. Then you have dichloromethane here, right? So basically this is a concentration series looking at like concentration blob. And then this is kind of a temperature series, like dropping the temperature towards the UCST, like there's a phase separation point, but it's all at 25C, right? 21C, I think they said. Anyway, then they go, so this is dilute in a temperature series, so a thermal blob. And then they go to, and then this is a concentration series, and they go through three concentrations: dilute, semi-dilute, and then concentrated. Concentrated meaning that you've gone beyond your concentration blob. So you have power, you have Gaussian at large scale, and that eventually eats to the point where you're at the Kuhn length, right? So going across this way, or going up this way, you'll get to the point where you're at the Kuhn length, and they call that concentrated. So semi-dilute between the two, dilute, semi-dilute, concentrated. So they have all three. And they go across solvent quality with all three too. So it's kind of a nice study on something that might have some use for processes, kind of interesting. So overall, it's a pretty good package. The main problem is obviously it's not going to work, to do this. So this is what they get out of it. So it's not, so you expect about 110 nanometer particles. So this is 200, so 10's like a little, so kind of one of these smallest possible things is probably one chain, possibly. Maybe absolutely the smallest thing you see, it could be one chain. then you got these other kind of globule things that form. So basically, it looks like this. I mean, if you glance at this, there's no difference between any of these, right? So basically, they claim there is, but and they all right. So they even get like maps of molecules per particle versus concentration in the PPPO in the dichloromethane, and then molecules per particle is a function of the quality of the solvent, like putting more heptane in. So they get results that look pretty good. The micrographs, I don't see exactly that they support that, So, but nonetheless, it's a pretty good paper, actually, on reading it for like 5 hours, which is what I ended up doing. It's something that should have taken like not very long to look at, So each one goes through the kind of blob stuff, each of these. So they start out, and that's the phase diagram, that's the stuff. And then they start out by doing the concentration series, looking at the concentration blobs. You expect to see, so it's just this stuff, this PPPO in deuterated solvent. So you're not going to see the blob, it's going to just be missing. It's like the fleece thing. So you're just going to see, as concentration goes up, you see the fleece, then you zoom in, you'll see the fibers. The denser the fleece, the further zooming you have to do to find a fiber, right? Until finally you can't see a fiber at all. I mean, you just see the persistence, the Kuhn unit of the thing, right? So that's what this data shows. So you see, so you take concentrations proportional, I mean, intensity is proportional to concentration, and then the contrast factor squared, right? So you have to remove the concentration, otherwise it just goes up with concentration. So you divide by concentration. It also subtracted the background, and then they have good solvent scaling. That's 5/3 minus 5/3 slope. That goes through all the data after it's reduced by concentration, and then this part drops because that's where the blob's showing up, and the tailover point moves to the right, and this is 1 over size, so it's getting smaller. So you're basically seeing that the blob eats the thing. The blob is eating the city or whatever. So the thing's chewing up the chain. Finally, it's just Gaussian at the bottom, and it'll just be completely flat. Right, they don't get to that point, but so that's the idea of this one, right? That's kind of this, they call it I. He calls it something I call it like regime, or he calls it isopleth I just call it regime I. So he's got regime I, regime II, III, and then IV, right? So this one's the solvent going bad for dilute, that one's going to concentration, this is semi-dilute, that one's concentrated. He's trying to find the magic thing where he's going to get a single chain come out of his machine. That's the point of this, I mean, again, like, it's not proven that that's going to actually work for germ warfare detection or something, but basically, I think that's the rudimentary idea behind this, like why they chose this polymer. Also, it's got a pretty good phase diagram and pretty well behaved. So there's some issues here that I didn't exactly ask about, but one is he talks about, so you have a chi parameter for the system, but you have 2 solvents, right? So you assume that the 2 solvents kind of act like one solvent, but actually there's a lot going on in a ternary system like this. It's not that simple at all. So why it would even work? And he mentions in the paper that sometimes you can take 2 non-solvents, mix them, and it can become a solvent. And you can take 2 solvents and mix them, and it can become a non-solvent. So it's not, obviously there's associations between the dichloromethane and the heptane and the polymer. This guy's polar, this guy's non-polar, this guy has polarity and non-polarity. The dichloro, when it meets the heptane, is going to organize around it. So you're going to have something like the hydrophobic effect. In other words, organization of these little polar things so that the polarity goes away from this guy means that these will kind of crystallize around it or organize. And that means the entropy changes. So the free energy of the system changes. Same with this guy interacting with the ethoxy, with the ether group. And then the heptane might have some association with this business. So all this kind of organization business is not accounted for in chi. Guy's forgetting about all that. So you're saying I can just call it all like a number. It's complicated, actually. So it's like, you don't expect that the results going to be so clean in this, but they are pretty clean. I mean, this thing works fine. Oops, right there. This guy works fine. In fact, he goes over here and like we just did this last class. We got like 3/4 power law for the concentration blob, and they get that, they get exactly that. So that's pretty nice. So when they get to the semi-dilute regime above C star, then they see that this guy drops with the 3/4 power law. Sweet. They have the same thing here with the blob size. This is reduced by RG. So that's pretty good. And then the other thing they see is kind of weird. Like they're going across, let's see. This is, let's see, C is change in Lorentz exponent M. So this is the scaling exponent, which is 3/5. Like you saw, it was 3/5 in all these things here. I mean, the data kind of looks weird where he plotted it. What they could have done, you can bin the data. Like you don't have to show every data point. You can sum up every 100 data points. So he's got about 500 data points. To sum every 20 data points, you get 1 point. And then it would look, and then you can reduce the error in those things by that, and then you'd get just a nice thing. You could kind of resolve something here. So basically he's saying though that there's a change in the slope in this data, because this goes to 20% PPO, and this is that's 20% here, right? So somewhere in the last few curves, there's supposed to be a change in the slope where it goes to Gaussian, which maybe you can see it could be there, like it's a little bit steeper. It would be like 2 decades by 1, so it's kind of close to that anyway. So he claims that happens, and it's this like discrete switch, boom, it happens, which isn't supposed to happen that way, but so he shows that it does. I'm not sure it's he, it's probably she. I think it's a she. O'Connell, let's see, hold on. Solve that. Roisin. I think that's a woman. I'm going to say it is. So anyway, so you got that business, and then this is the part two where they go across the bottom, right? So that's going to pour solvent. So this is where we expect what we got last week, like a thermal blob, right? So, but they don't. He claims, so he just plots intensity here, and here he plots intensity minus the background, and the concentration doesn't matter because it's the same concentration across this. So he doesn't get rid of this background thing, so that's a problem. Like you can't resolve. So this is, you're expecting to see the collapse, like the Gaussian part show up here, and you can't resolve it because there's a background in it. So anyway, I went and digitized some of it and like saw if that was feasible in this stuff to see if there's if you get that Gaussian at the high end like you would with a thermal blob, with a thermal blob thing. Let's see now. This won't show up for you guys on the thing, but basically, oh, and the plot I'm looking for isn't here. Let's see, graphs. This thing. So this is, that's kind of, so you can see, so the data original that he shows is the green. I went in, so I used that Igor Thief thing, which is in here, and then it comes up, and then you can just paste in the graphic and then do this digitate. It tells you how to do it. There's an instruction thing. All right, so you get these points. Works pretty well. So you got, that's the data points for the different. I did pick 3 out of the 5 he did, or she did. And then I subtracted off kind of what I thought was the background out here, a little bit less than that value. And then I kind of was looking for a -2 out here, and I got it. I mean, I got it to my satisfaction. Hard to see the green one, but.
So are the lines what the
lines are the subtracted thing. So the dots are the three. So anyway, it goes kind of two. That would be like a thermal blob. And then it goes 1/5 over here. So that's what we saw in that transition, is that blob size. The problem is, like, when you go, it isn't really high quality, but this is 0 heptane. Then you're increasing heptane. So that should be the best solvation condition. That means this blob should be the smallest. That's like the high temperature for the UCS, or the high temperature for the UCST. Then this is going to a lower temperature. It looks from this that goes here, then it goes there to a smaller size, and then it goes back up. You know, and I only did 3 of the 5, but basically it's not showing a trend, and the trend that it's showing is in the wrong direction, which I think probably has to do with this kind of, like, it isn't exactly that predictable as a temperature. It's like the organization, who knows what happens. But there is a signature of 2 and 5/3. I mean, that could be why they didn't bother to show this.
They did do it and then they saw it didn't work.
Well, all right, yeah, so that's likely, I guess. It's hard to tell, pretty hard to tell, but they do, all right, so they do a fit that includes that thing. You can't see it, but it's in there somehow, and it includes some number for a background. So they do a fit to that business. This is for the 2, this is for 3. So this one is the this is the kind of the dilute one, and this is a semi-dilute one. We expect to see like 2 and then goes to, or something happens here and it'll phase separate. And then I don't, 2, 3, and 4, I didn't really ask much about except to compare. So they show, let's see, somewhere here they show the results from this. This is from isopleth 2. So they have this blob size, which should be a thermal blob, and then the concentration, and they show it nicely marching up. So I just showed you like the first one, the middle one, and the end one. I guess I had more than 5. So, so they do show that it sweeps up and down though. So maybe if you digitized all the data, then you could get this same plot out. But they do the fit. They get this number out of the fit, and you can see the fit isn't giving you a lot of confidence because the transition number and the slope that you're looking for isn't even in the data. So the background washes everything out, that you can't see what you're trying to fit. It's like feeling around in the dark. And then when the error bar looks good, so when it matches up with the background, essentially, then you take the answer. So that's not very convincing fit, really, you know. But anyway, they do get this number and it behaves the way you'd expect it to. Let's see, as the heptane goes up, it should be that the that the thing becomes more and more, yeah, so this should get larger as the temperature drops, and then becomes Gaussian when you get to the critical point. So the behavior they have is pointing towards how it should behave, except we don't have a functionality in concentration and non-solvent from the theory. Like, we don't have any idea what that, so they're just saying it's linear. Actually, it's a sigmoidal behavior, you know, and it's going to go rapidly up at the end. So that would seem to be more reminiscent of something about clustering of the dichloro around the non-solvent, the heptane, and then like somehow there's like entropy things going on and all kinds of stuff because it's a complicated system. So, but they say it's a straight line. I mean, a straight line, this should go to infinity when it reaches the critical point. So a straight line is not really very good. It should be 1 over that thing versus concentration to begin with, but because you're looking for that thing 1 over that to go to 0 at the critical point. It should go to infinity in extrapolation to the critical point. This thermal blob size. Anyway, so that all fits together pretty nicely. I mean, I don't really like some features of how they did it, but basically it's a pretty nice picture for a dirty system, you know, and it fits directly with what we're talking about in class. There's just some questions about this. When they finally get to the concentrated and doing this thing, then they see like 2 size scales show up, which is convenient, you know. So this is probably like power 4 here for like some gigantic thing, like those giant droplets. Then this stuff out here is the single chain separation. So they have the 2 phenomena going on. You can see it in the neutron scattering. And, that kind of ties in with what you see here. In other words, there's little things and there's some big things. And the big things are those big things they see here, the tail up here, and then the little things are the things you wanted, like this single molecule nanoparticles. Right, and then and again, like they map out like molecules per particle thing. So it's a pretty good paper. I mean, it's kind of good to look at. And it's Higgins. These other people I don't know, but they're probably, I mean, they're all Imperial College except one's at this Beauchem, which is a German. Do you know what Beauchem is, Mike? It's like a German, I think it's a German polymer company. They may have been a spin-off from some other like BASF something, who knows what, but yeah, it's some polymer company in the Netherlands. So anyway, so that's what this thing is. So that, let's see what the phase diagram, blah, 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 blah. Region 3, explain what you expect to see. So that's kind of like region 1, it's kind of, you're going to see concentration blobs. They're going to show up at large size. What is it?
Beauchem's logo is like exactly
It's that.
the molecule.
The
that
PPP.
you're
Is that right?
talking
The
about, the
PPP.
paper,
All right, so they
yeah.
probably make breathalyzers, yeah. Like the
They
breathalyzer
must
company.
make the PPPO they use in their stuff.
No, that's where I've seen it. In Germany,
Yeah.
when you walk out of the bar, they have these things they'll give you to check to see if you can drive your car or not.
Oh, wow.
Yeah, I think I remember a long time ago.
Right.
So they probably make those
Their
things.
logo is that polymer.
Is that right?
Yeah, so you wonder
Okay,
why that person's in the paper.
Yeah, okay,
That's
so
fine.
it's not a student that graduated, they actually paid for the thing, like, so they see what they're doing. That's pretty funny. Okay, I'm glad you did that.
Takes about 2 seconds to
Yeah,
figure that out.
Yeah. All right, so anyway, one is going to be this concentration blob, so you expect to see the thing disappear at the large sizes, like the fleece thing. 2 should be that it goes Gaussian locally, and they kind of demonstrate that, and it should go up. The blob size should grow with concentration, like just like dropping the temperature for UCST. And they show that happens, but when I checked the data, it didn't seem to show that. Then 3 is this semi-dilute region, and that could get kind of complicated because you have both 1 and 2 going on at the same time. I mean, so 3 is kind of up for grabs, and 4 is totally up for grabs. So I didn't mention 4. So some kind of cartoon of the chains, so that this could take a long time, I guess. I don't know. Then he shows the log-log plot for region. Wisely plot I by 5. That's because intensity goes with concentration. And then they lay on top of each other when you divide out the concentration. And then the knee is this blob size thing. And then if you do 1 over Q for that knee, you should get that business we saw before, the minus 3/4 slope. Oh, and then this says like derive that. So just go back to the class notes. I did that in class, the 3/4. Then region 2, function of reduced solvent quality. So I digitized that. That's over on the web page somewhere. I put that it's in Igor again. So figure 4B digitized. Hopefully you can look at that if you want. This is just kind of do whatever you can do with the results. Like he's got this whole picture, and then how does that match up with this machine? You know, like how does the whole thing fit together? That's kind of what 4 is. So it's E5. Micrographs, the connection, the 2 sizes, single chain, is that possible in this thing? And this is what he did of any use? That's an open question, you know, because so I mean it's kind of an open question if what he did was any use. In the end, like what do they care about? This is the problem with, you know, this kind of thing, that like in the end you want to make these, maybe you want to make the smallest one you could make, maybe not, you know, maybe if you actually make the 10 nanometer particles, like how are you going to keep them apart? Like, so you can make 10 nanometer particles and they could pack into a crystal, you know, and then you have no access to the surface anyway. So that isn't exactly what you want. Maybe isn't exactly what you want. Like this whole thing that they showed a picture of, like how's something going to diffuse in to get trapped in it? So it might be that you want something kind of aggregates of those 10 nanometer things that would have open space between it, or somehow even the larger ones might be better, or a mixed breed of the things might be better. You can't tell exactly what's the best way to make this thing, but right, controlling it is something you're going to need anyway. So maybe it's useful. I doubt they're going to get a patent. Maybe they'll get a patent. There are patents on things exactly like this for membranes. So say like, oh, we go this route, and then you get to that because of this, and then we get this membrane that's like super membrane to do separations, right? And then they patent that route. So it is, and then they also patent the material at the end too. So in case their theory about how it formed isn't right, they own the thing too. That's a stronger patent, is to have the patent on the thing, right? So the pathway is more rewarding, but the actual thing is what you want. Right, so it's that business. Then in doing that, I fished up some other stuff, So Grossberg. So in physics, they do this weird thing. Like they'll publish a paper. He submitted this paper on February 1st. By the way, that paper was just published like yesterday or something, that other paper. And this paper isn't published yet. It's not even accepted. So he submitted it February 1st to condensed matter physics or something, soft part of it. And then in these journals, they give you the option, you can print it before it's published, so that because it can take a year or two to publish it, so you just don't care, like no one's going to steal this idea. So you just publish it. So you can see Grossberg's now at, the guy that wrote that book, Giant Molecule, is now at NYU. Like he came here, we could have had the guy. Of course, he's not rich or anything, so maybe there's not that much loss, but he went to NYU instead of coming to Cincinnati. And then he's still working with all these Russian guys that are kind of doing this collapse stuff, right? So this chromatin is, I don't remember what chromatin is. It's got to do with the way that the DNA like folds around a rod or something. I don't remember exactly how this works. Chromatin's a protein, then the DNA wraps around it inside the someplace. Something about the nucleic acids somehow interact with protein structures, and they form these kind of helicals, something or other. Yeah. Right. So anyway, so he goes through this paper about theoretically, if you had blobs, tensile blobs, so you stretch it out, and then how does that work in this 2D space, like a 2D space tensile blob? Normally you have the thing floating around, you pull on it, it's like a string. The big parts straighten out first, the small ones straighten out last, right? So okay, this is in the context of chromatin like going on to this rod like anyway, you can see this can get pretty involved, and these guys are really enjoying doing this stuff. So then they say, I can do a rod. How about an ellipse or ellipsoid? How does it do with the aspect ratio? This is a picture of what chromatin would look like this ribonucleic acid twisting around a protein shaft, right? Then so he just goes through here like every possible kind of way you could stretch something in different dimensional space.
So is this all like theory and models?
It's all just theory and models. There's no actual chromatin involved here. Yeah, and could be a lot of it is like computer simulation, but basically this is just theory. I think this is just saying like, I can do these scaling theories. I can figure out what the size of the thing's going to be, what the force on it is. How does this kind of folding thing happen? You can predict like general concepts of it. Anyway, I didn't do that paper. So that one's there. Just thought I'd put these up because these were options. So this is a case where you make a gel, right? So you have the network of the gel are tied together with cross-link sites. Then along the gel, you put, this is also just a conceptual thing, although you can make this, you could make this. And all right, the Japanese have been making these rubbers, these bottle brush rubbers, it's like the latest craze in Japan for like new materials. And they think they can get special properties out of this kind of bottle brush network thing. Anyway, so this isn't totally, and it's companies that are doing that. It isn't government, So these people are Russian, I think. I think these guys are Russian. But this is a topic that's really popular in Japan. Knowledge mints. I guess soft matter gives the macromolecules puts your location at the end, you know. Yeah, so they're Russian Academy, Petersburg. So anyway, so they're looking at how same kind of thing like the stretching. This is basically the tensile blob stuff. It's the same thing, like you stretch out because they're crowded together, they stretch out, get the force. You want to calculate the length of those, then figure out how the rubber behaves when it has that kind of stuff in it. And they get phase diagrams for it. That's another thing. These are all like within the past month, right? So it's like, it's kind of surprising. I thought I'd find like maybe a paper within the past 5 years or something. But
You're like, "Ah, yesterday.
these guys are cool though. These guys are doing something really cool and worth looking at, although it has little to do with what we're talking about. So they're at Kobe University. So Kobe is where Procter & Gamble does stuff in Japan. They have a huge lab there. And Kobe is the place. I knew, like I looked at this and I Googled it and I found out, yeah, that is the place people were talking about. It's in the south part of Japan. Anyway, so they take, so this is they take an AFM and they stick it in like a tube flow system, like Pucelle flow, and they can put the tip down different lengths and get the velocity from the force. They can get the velocity of the fluid, like that's the velocity profile across this gap. I thought that was pretty sweet. Like you can get that with an AFM. I mean, I don't know how else you would get that. I mean, this is theoretically what the velocity profile would look like. You see it in your books about flow, but how do you actually measure that, you know? So these guys had a spare AFM and they knew how to take it apart and they just stuck it into this flow cell and they could get that. So A, that's pretty cool. I thought that was really cool to do that. Then B, they stick polymers onto the tip, which has been done before. So people will take like the tip. So they have like DNA stuck to a surface. Then you take a gold tip and the tip of the DNA, you put sulfur on it and it bonds with gold. So the sulfur attaches the gold and they can lift up and you can stretch the single polymer chain back and forth. Sometimes you get one chain. Most of the time you get a bunch of chains, right? When they get one chain, they can kind of tell. Because when they have a bunch of them, they stick slip, like some of them will break and others won't. So finally they end up with one and then they can do this thing. All right, so that's probably 20, 15 years old doing that, maybe 20 years. This is something like that, but they glue onto you can see they're using PEO, polyethylene glycol, PEO, water soluble, or it can go into glycerin too. And then they subject it to shear. Then they can stretch the chain. So they make tensile blobs of the chains on the tip of this AFM. You can see they're stretching the things out. Then they go into like tensile blob modeling of the thing. You can see this tensile blob gets a lot of mileage. Like it's kind of a nice little theory. You got the force, you got the length, everything fits together pretty nicely. And KT is the other opposite thing. Anyway, so they did a study of that. I thought that was pretty cool. That's also like this month, you know. So there's a lot of other papers. Basically, those are the ones that were the coolest, I thought. But so this one, particularly, I really like this paper. Like, I think that they like really came. Maybe someone else has done this already. I didn't really read the whole thing, but I like the idea of that paper. So anyway, that's what I got for today. Guess we'll quit early, but any questions, anything? Like, hopefully that homework's all right.
Interesting way to stretch one individual.
Yeah, it's really cool. Like this is the more I glanced at it, I thought, oh, that's pretty interesting. Then I realized they got this profile, you know, without the polymer, that alone is really cool. Like you could do that. And then like they stick the things on, yeah, and then it's just this tensile blob. It's pretty nice work, like to do that. I mean, to come up with that idea, I'm sure they didn't, maybe they stumbled upon it, I don't know, but basically just this intuitively you wouldn't think you could stick an AFM into a flow field to get the flow profile from it, you know, like it's not an intuitive thing. So I think it's pretty nice that they kind of got that. I mean, but Anyway, that's about it, I guess. I don't know what else. I don't really want to do the collapse thing today, like, because we do have 10 minutes. Probably just call it quits, because you got to do that homework and you'll be jamming too much into it, I think. So,
See if,
see if the thing
Video.
downloaded. Yeah.
I
that's a
think
good
I think I
thing.
saw it, that change pop up.
All right.
Well, that looks like that popped up. That's probably 2/2/16. Yeah, that's 2 days ago.
Do you see it somewhere?
It should be the MP4 file. That one
All
right
right.
there.
Okay.
And audio. I don't think that's separate. I don't know how it works.
Or it should be.
Yeah, it's MP4. The other things are just this. It comes with an audio and
It's separate audio if you wanted it.
Yeah, and if it's got also like any chats anybody came up with are there.
That file sizes, yeah.
It's
Okay.
The file size is huge, and that's not everything.
That's not an hour-long
Right.
Zoom call, yeah.
I should quit what I'm doing now though.